class, welcome to the next section in chapter 11, 11.3. Today we're going to actually talk about how to solve um, a differential equation. So we're going to go over two methods today, separation of variables and an integrating factor. And these both work for first order equations. They do not work for every first order equation. However, these two together will take care of most of the first order equations that you should run across in your exploration of differential equations. So let's go ahead and move forward. So first, let's talk about separation of variables. Separation of variables is when we have two functions that are being multiplied times each other, where one function is completely in x, one function is completely in y. So the derivative of our solution function is can be seen as the product of two separate functions, one totaling x, one totaling y. Sometimes we have to do some manipulation here, and we might have to factor some stuff out. We might have to get a little bit creative with our algebra. In order to separate these into two separate functions, they might be entangled in some way, and we might have to untangle them, right? So you can't always look from first glance and say, oh, this is a separation of variables problem. Sometimes you have to manipulate one side of your equation a little bit, okay? So I cannot use separation of variables if my function does not look like this. Okay, they have to be separable because it's called separation of variables, right? So if I can do this, then I can separate the two variables where I get everything of x on one side, everything of y on the other side, including these differentials, right? So remember, we're allowed to split differentials because we're not really, this isn't a course for derivatives, this is a course for integration. So in order to find a first derivative function, usually you have to integrate something, okay? And so what we're going to do is we're going to pull this derivative apart so that so that differentials um, move to different sides, right? So the first thing that I would do is I would separate this differential, and I would get d of x on one side and dy on the other side. Then I'm going to separate the two functions as well so that I divide both sides by fy and g of x stays the same. Now I have something that has a differential of dy, and the function that's present is a function of y. And then I have a function of x with a differential of x. So then I can now, at this point, just differentiate both sides. Okay. So here I'm just renaming my function just so it's easier to see. But it's just another function in y, right? So once I have my y's and my x's separated, I can integrate for y and integrate with respect to x. Okay. And then my function is some large function, right? This would be a capital H, right? Because it's a small h. So when I integrate, I get the derivative function, basically, the antiderivative function. And then here, this little g turns into big G plus my constant of integration. I don't need a constant of integration on both sides. Let's say I did have plus, let's say this was k, right? Constant integration from this side. Well, if I move that constant with this constant, it just creates a new constant. I only need one constant. Okay, a constant plus a constant is a constant, so we only consider one side as having a constant from integration. Okay, we only need one. So once I do this, then I can then solve for y of x, right? So let's go ahead and do an example. So let's say I have u prime is 1 plus t to the fourth over ut squared plus u to the fourth t squared. So here, this from first looks does not look like something where it's a function of u times a function of t, right? So my goal here would be to try to separate them if possible. Okay, so I would do a little bit of work and see if I can separate them. If I couldn't separate them, I would move on to another method, right? The integrating factor method, which we'll talk about a little bit later, is actually pretty easy to identify. So it's easy to tell when it's that method that I have to use. The separation of variables, however, as you can see in this example, sometimes you have to manipulate things a little bit. Okay. So the next thing to do is going to probably rewrite this u prime as du over dt, right? So this function is being differentiated. We're talking about the rate of change of u as time progresses. That's why u and t is here. And so we rewrite this as du dt. Okay, so we'll first start with our function. I would rewrite this again as du dt. Then I want to try to separate this stuff. Okay, in the denominator, you can see I have a u in two places, right? I also have a t squared here and a t squared here. So maybe instead of trying to pull out a u on the bottom, I'll pull out a t on the bottom. Okay. And so now, even if you can't see it, it definitely looks like something where it's a function of t times a function of u. The function of t is just 1 plus t to the fourth over t squared. The function of u is just 1 over u plus u to the fourth. Okay, so I can separate them into the respective u functions and t functions like this. Okay, and then what I would want to do is, well, the dt needs to come over this way, and that means that the u function needs to go over here. So I would divide by this, or easier way is to multiply times u plus u fourth on both sides, and I would multiply by dt on both sides as well. And then when I separate my variables, now this is what it looks like. Now it's very clear. I can just integrate both sides. If I throw an integral sign here, well, it's an integral with respect to u. And if I throw an integral on this side, it's an integral with respect to t. So I'm still being equal because I'm doing the same thing to both sides. I'm integrating both sides, and they both already have the respective differentials. So that's what I'll go ahead and do. I'm going to integrate u, and I'm going to integrate the t. Okay, so I threw my sign up. I changed this to t to the negative 2. Okay, so really what I did was I separated this because that's going to be the easier way. Instead of trying to find a u sub, I'll just separate this into two polynomials. So 1 over 2 squared and t to the fourth over t squared is just t squared. Okay, so I kind of simplified that so I can integrate it. These are just two polynomials. Very, very, very easy to integrate. This is 1/2 u squared, 1/5 u to the fifth. This is just going to be negative 1 over t to the negative 1, or just negative 1 over t, I should say. And this is going to be 1/3 t cubed. Okay, boom. You can see here, just to show you what I mean about having a constant on both sides, right, it's an indefinite integral, so I have my constant of integration here. Here, I have my constant of integration. If I just move this over to here, okay, a constant minus another constant is just a constant. So I would just replace this C2 minus C1, and I'll just call it C for the new constant that comes up when I subtract them, right? Very, very straightforward. Okay, remember what we're looking for, okay? I have u prime equals something. So ideally, my solution will be u equals some function, okay? So my goal here is to solve for u, okay? So I want to isolate u and get everything on the other side. However, I can't do that because there's no way to get u alone, right? This is 1/2 u squared, 1/5 u to the fifth. Even if I factor the common factor of u squared out, I still have some u stuff on the inside. There's no way for me to just say u equals some function of t. Okay, there always has to be more than one u present in order for that to happen. So what that means is I cannot find an explicit function for u, meaning I can't find u equals boom, everything else, an explicit function for u. So since this is not an explicit function, it's impossible. This is an implicit solution. Okay, I cannot solve for it explicitly. So this is an implicit solution, just like implicit differentiation. You see y times y prime somewhere, all this kind of stuff. It means I can't find y equals something or y prime equals something. It doesn't work out for the way that my equation is structured. So since I cannot find u of t explicitly by itself, right? There's multiple u's here. I can't get just one. This is an implicit solution. So an implicit solution, you want to just try to work down as far as you can. Okay. Let's do another example. Take the IVP. dy over dx is this crazy stuff on top, this crazy stuff on bottom, with a boundary condition of y root 2 equals 3. So if I'm looking at this, I'm kind of saying to myself, well, dang, how am I going to separate this? I don't have a y everywhere on top, but I do have an x everywhere on top. So on the numerator, ideally, I would factor out x. So I can pull out x, and I can pull out this denominator of x, and then all my x's are alone, and then all my y's are then now alone as well, right? So I got this polynomial, this quadratic in the form of y. So same thing here. I'm going to multiply both sides by dx, so that dx cancels here, and the dx is here, so basically I'm moving it over, right? And then I need to move all of my y's over, so I'll divide it on both sides so that I move this onto the left-hand side of my equation, okay? This is just a perfect square, so we'll rewrite it as a perfect square. And this is x squared minus 1, which is not a difference of squares, so we'll just leave it how it is here. And then we got to integrate both sides, okay? Um, Here, it might make sense to take u squared as a u substitution. It's probably the best way here. Okay. Here, I'm going to take u minus 1 for my v substitution. And then u is x squared minus 1. We'll just take that whole thing. Okay. So dv is going to be dy. Okay. Du is going to be 2x dx. And I have a x dx already, but I don't have a 2, so I'll just divide this 2 over, so I know exactly what x dx is. So half of du is x dx. So I can go ahead and make my substitutions. So this turns into 1 over v squared dv. This turns into 1 over, 1 half times 1 over u du. Okay. So this is just v squared. This is going to be natural log, right? So then here I'm going to have negative 1 over v, and this is going to be 1 half natural log of u. Okay, negative v to the negative 1 power, 1 half natural log absolute value of u plus c. And again, this c takes care of the constant from this side. So here, there's only one v present, not like here where I had different powers of u showing up. There's only just one v with one power. Doesn't really matter what it is. There's only one v, so I can isolate this v. So what I'll do first is I'll go ahead and make everything negative. Okay. Well, first let's substitute. Okay. Ideally, I would still solve for v here, but let's go ahead and resubstitute first. Okay. So I got ahead of myself a little bit. So we will plug in y minus 1 for v. So this v to the negative 1 is 1 over v. So negative 1 over y minus 1. And then u, I know, is x squared minus 1. Okay. So now I want to just solve for y. Okay. So first thing I'm going to do, again, now is change the sign everywhere. Okay. Um, okay. Or I could do that. I guess that's fine. So here I'm just going to multiply by y minus 1 on both sides. I'll distribute this 1 half term through, or I'll divide it actually, and then now I can just add 1 to the other side. Okay. So again, I multiply both sides by y minus 1, and then I divide by this answer, so I move it over here. Okay, and then I can add 1 to both sides, and now I have y equals everything else. Do I want to simplify this? Yeah, I can. I can go ahead and make this a little bit simpler, but this is also fine as an answer as well. Okay. Plugging in my initial conditions, right? Plugging in -2 and getting out 3 means that I'm going to plug in negative root 2 here, and I'm going to plug in 3 for y. Okay. So, okay. Oh, it looks like I got ahead of myself. So, okay, what does that look like? So if I plug in root 2 here, that's squared. That's going to give me 2. 2 minus 1 is 1. Natural log of 1 is just 0. So all of this goes away. So then what I have is -1 over c left over plus that 1 equals my y. Okay, so again, don't feel bad to do a little bit of side work here. So in order to solve for c, first I will subtract 1. Okay, I'll subtract 1 and I will get a 2 here. Then I can multiply by c, and then I can divide by the 2. So I get c is -1 half. Now I'm not done because I still got to come and put it all together. Okay. So my y function is -1 divided by 1 half natural log x squared minus 1 minus 1 half. I can simplify this a little bit. I can pull out this 1 half because it's a common factor, and then I can rewrite it so that the 2 is on top. Okay, because I have a fraction in the denominator, so it gets moved to the numerator. Now I don't have a fraction in a fraction, and I don't have any issues. This would be the correct form here. Okay, so since I could solve for y of x directly, explicitly, then this is now an explicit solution because I was able to say y equals this thing. That is how we do separation of variables. So now let's talk about the next method, which is called the integrating factor. So these two methods together make up the majority of the methods of us trying to solve um, a first order differential equation. However, there are many other methods that we employ also for first order. Okay. If our differential equation has the form a function of x times the first derivative of y plus a function of x times y equals some function of x, okay? Then we can use an integrating factor. So the first thing that we do is we want to get the y prime alone. So I'm going to divide the entire equation by f of x, okay? That leading function that's here. I keep the y prime term, but everything else I divide by, and it has to be x, right? There can't be any other y's here. So again, this is for linear functions. So I'll divide everything by x, so I get new functions here, right? Or by f of x, I'm sorry. So I get new functions for this f of x, this g of x, and this h. Okay. Now we're gonna call this new function g of x over f of x that's been divided, p of x. We're gonna call this new function on the outside q of x. Okay. So my function is going to be y prime plus some function of xy plus some function of x also, right? No y's on the outside, on the right hand side. So basically what all I did was I got y prime alone in front. Okay. Second step we're going to do is I'm going to multiply the entire equation by what we call the integrating factor. Now, in order to find the integrating factor, I'm going to take my function, I'm going to take e, and I'm going to raise it to the power of the integral of this new function p of x. Okay, and I'm going to integrate it with respect to x. And I'm going to simplify it, and the answer that I get, I'm then going to take that value and multiply it across my entire equation. Okay. So e to the integral of p of x with respect to x times y prime times the px times y and times that q of x function. Okay. Now what this does is it allows me to undo the product rule. Okay. It allows me to undo the product rule. So what I have here on the left hand side is the product rule. Okay. So if I take the product rule, if I differentiate two functions that are being multiplied, I differentiate the first, multiply times the second being alone. I add to that the first function being alone and the second function being differentiated. Here, this is actually opposite in order. Okay, so if this is the function, okay, and y is my other function, then this is the product rule. So I would leave the first function alone. Or I'm sorry, I would differentiate the first function, okay, this e to the integral of p of x d of x. If I differentiate that, the the derivative of the exponent gets brought down. And so that's just p of x times the regular function. On the second half, the first function gets left alone, and I differentiate the second function and get y prime. Okay. So this is just the product rule. And I try to walk you through this, but it's hard to see it until until we can see it. So I'm gonna undo the product rule. I'm starting with this right here, and I want to undo it by using the left-hand side of the product rule. So I'm undifferentiating, basically. Okay. I'm not integrating, not yet, but I'm undoing the product rule. Okay. So I'm going to have the derivative with respect to x of this integrating factor times y. Okay. And on the left-hand side, I'm just going to have the integrating factor times q. I'm literally not doing anything to it. It's just coming along for the ride. So if I were to do the product rule here, okay, so this is where we should kind of move backwards a little bit. If I do the product rule here, I integrate this first function, okay, which is e to whatever it is there by itself, and then the chain rule says I take the derivative of the exponent and multiply it times my function. So this first half here is from the first part of the product rule. So I take that and then I just multiply it by the second function. I add to that the first function being left alone times the derivative of the second function, y prime. So what I have here is the product rule, and after I multiply by the integrating factor, I have the product rule on the left-hand side, so I undo the product rule. I'm going to differentiate with respect to x, and I'm undoing it. I'm putting it all together inside of parentheses. Okay. So now what I can do is I can integrate both sides of this thing. Okay. I'm going to integrate both sides with respect to x. That's going to make this derivative portion fall off, and then this is just going to get integrated. Okay. So this is going to stay just how it is. Okay. All of the integration just cancels with the differentiation. Okay. And the left-hand side, the right-hand side, I'm sorry, here gets integrated. So I'm going to take the integral of this whole function, and then the uh, constant term from uh, the definite integral is going to come out as well, plus c. Okay. Once I do that, I would want to solve for y by dividing both sides by this integrating factor. Okay. And now I have an explicit solution for y. To be honest, if this makes sense to you, you can solve all of the integrating factor problems by just following the formula. Okay. The process of solving integrating factor problem is these steps 1 through 5 that I just walked through. So by doing this in general, we've come to a solution that will work every time. It's applicable, but I do want you to learn how to do it through the process. It's actually very fast. I know this seems like it's a lot, but these problems, the integrating factor problems, I think they're actually pretty fun. I like doing them. They're not that difficult to do. Okay, so let's go ahead and do an example. I have x squared plus 1 times the first derivative of y plus 3x times y minus 1 equals 0. And I have a boundary value point of plugging in 2 and getting out 2 to my solution. So this doesn't exactly look like what I need. Okay. Remember, some function of x times the first derivative. Some function of x times y equals some function of x. Here, you might think at first glance that this is homogeneous because it's equal to 0. But once I multiply this 3x across, I'll have an extra negative 3x term here that I can move across. So this is actually non-homogeneous. Just because it's equal to 0 does not mean that that's what it is. You actually have to be able to manipulate these things a little bit first, and then you can talk about what type of function they are. So that's the first thing I'm going to do is just distribute this 3x across. Okay, I don't need to distribute this y prime across x squared because I want to get this thing along in front of everything else. But I will distribute this 3x so that it is in a proper form now. A function times y prime, some function in x times y equals some other function in x. So now the next step was to divide everything by this first term. So I'm going to divide everything by x squared plus 1. Okay, so that gets my y prime in front all by itself, and then I have a denominator of x squared plus 1 on the other two terms. Okay. From here, I need to find the integrating factor. This is my function p, this is my function q. The integrating power is e to the power of the integral of this function p here. Okay. So my integrating factor is e to the integral of 3x over x squared plus 1 with respect to dx. So if I go ahead and integrate this, I can just make a u substitution here. U equals x squared plus 1. We saw previously that I had a very similar problem. Okay, so I'm going to get du equals 2 x dx for the thing here, and I can move the 1/2 across. Go ahead and sub all of this in. Okay, and this turns into e to the 3/2 integral of 1 over u du, which I know is natural log of u. Okay, and before I even substitute this in, I'm not sure which order I actually do it, but I know e raised to the power of natural log always cancels. So this actually turns into u to the 3/2 power. Okay, and then now I got to make in that substitution for u, which is x squared plus 1, and that is my integrating factor. So what I'm going to do now is I'm going to take this and I'm going to multiply my entire equation times this integrating factor. The first term, the second term, the last term. What that's going to do is for the second term in the right hand side, things are going to cancel out. Okay, so I'm going to go ahead and multiply everything in. X squared plus 1 means that there's a 1 on the bottom. I have 3/2, so 3/2 minus 1 leaves me with 1/2. right? So that's why I have this 3x from the numerator, and then x squared plus 1 to the 1/2, or you can think of it as the square root of x squared plus 1 as well. And then on the outside, I have the same thing because I have also 3x x squared plus 1. Okay, here I have this y. Here I still have this y prime. The first term here was just y prime, so the whole integrating factor is here. Okay, so now, even if you can't see it, I have the product rule here. Okay, and the way that this works, right, as we walk through it here, it's important that you know which one is the first function and which one is the second function. So here, this was the chain rule from integrating, or I'm sorry, differentiating the integrating factor. Okay, this y prime and this y is just coming from y. So when I do this, I'm going to have y, and then whatever the integrating factor was is the other part. So it's the integrating factor times y is what was differentiated in order to get that product rule. So when I undifferentiate it, that's what I'm looking at. So I need my integrating factor, so x squared plus 1 to the 3/2 times y. Okay, and that is what's being differentiated. So if I were to differentiate this, I would get this left-hand side here. Again, if I differentiate x squared plus 1, okay, I'm going to have 3/2. I'm going to go down by a power, so that's the 1/2. And then I'm going to differentiate x squared plus 1, which will be 2x. So the 2 times the 3/2 will cancel the 2 and leave me the 3. And then I will have an x left over as well. And then the y would not get differentiated. On the other half, I would leave the first function alone and I would differentiate y, right? So again, if I were to do the product rule here, I would get the second part out. So I always have the integrating factor first and y second, right? So you don't really have to guess what this looks like. It's whatever your integrating factor was, and then y, throw this differential on the outside. Now I can integrate both sides, and what that does here is it just cancels with this derivative, okay? It, I don't actually integrate the right-hand side, left-hand side, I'm sorry. It just cancels this derivative notation. I do, however, need to integrate the right-hand side. So here, this is all convoluted, so the easiest thing to do is to make a substitution, right? Obviously, u equals x squared plus 1 is probably going to work best here, okay? So again, I get 1/2 du x dx, which works perfect, right? So this turns into 3/2 u to the 1/2 du, okay? My left-hand side, I'm not doing anything to it yet. I'm just trying to work out this integration. So then this, I know, turns into 3/2, and the reciprocal multiplies here. And so that cancels, right? Because this goes to 3/2, the reciprocal. So that cancels. That 2/3 that I'll end up with is going to be canceled with this 3/2. So I have just u to the 3/2 plus c. Resubstituting my u. So this is x squared plus 1 to the 3/2 plus c. And then I can divide both sides by this integrating factor so I can isolate y. And that's my answer. However, I'm not done because I do have an initial condition, right? So all I did was plug in u that I had back here, and that's the numerator portion. And this denominator portion is from isolating y, so dividing both sides by this integrating factor that was here. I cannot cancel this out. Actually, I can. Okay, I could cancel this out right now. In fact, that's what I should do. I don't know if it is what I do, but this should turn into 1 plus c over this integrating factor. I can separate this into two parts. Okay, see, I know myself well. So it's a lot easier to deal with it here. I have an explicit solution, as I did before, much simpler to deal with. So now I can use this condition that I have and plug in 2 for x, and then 2 for y, and then solve for c. So if I plug in 2, I'm going to get 4. 4 plus 1 is 5. So this is c over 5 to the 3/2. This is 2, so I would just subtract this 1. So I have 1 equals c over 5 to the 3/2. Multiply both sides by 5 to the 3/2. Let's actually do this. Okay, so minus 1, and then multiply both sides by the 5 to the 3/2, and I'm left with c on one side, 5 to the 3/2 on the other. So my exact solution is then y of x is 1 plus 5 over x squared plus 1 to the 3 halves, since this is to the 3 halves and the denominator is to the 3 halves as well, right? So c is 5 to the 3 halves, top and bottom is to the 3 halves power. So I can just say the whole thing's to the 3 half power. And that's my solution for the integrating factor. If I wasn't sure if this was correct or not, you know what I would do? I would take this and I would plug it back into my differential equation. I would take its derivative, plug it in here, plug in y here, and I would hopefully end up with 0. Okay. All right. I will see you guys on the next and final chapter where we talk more about solving, although we're not going to be solving any more first orders. We're not going to get too deep into that because the methods are much more difficult than these ones are. We're going to talk about the easiest way to solve second order equation, which I actually think is much easier than these ones. So see you guys on the last video for this section.